much, Kojik, and this is taken by many. Few guys from Hungary, Budapest, and guys from St. Andrews. So Kevin is also among the authors. I can refer back to the keynote. So the motivation behind the research is supporting structured parallelism in Erlang. We try to force the programmer to think in parallel, but rather than designing software in a structured way, we also would like to address legacy code that's written already, and we want to show how to turn it into parallel. So the focus of this talk is going to be a tool called parting, which is used for finding realizable components in a mostly sequential Erlang program. So this paraphrase refactoring tool is actually not just a refactoring tool, it's much more. It is first a discovery tool which allows us to find those places in the code which can be parallelized. Then it's a tool to make estimations and possible speedups and make suggestions to the programmer where it is most advantageous to do the realizing transformations. And of course, thirdly, we can assist the programmer to apply refactorings, automate refactorings with the tool. So in the paraphrase project, we have learned about the different skeletons that are implemented in the Scala library. At the current stage, we are focusing mostly on task farms and pipelines, but our work can be extended to other skeletons as well. So we would like to enforce a structured parallelism by allowing the programmer to introduce parallelism into the code using the Scala library. And we would like to assist this process by telling the programmer where to insert the skeleton and which skeleton to insert, and of course to try to assist the programmer to insert the skeleton as well by refactoring. The whole paraphrase project has much more ambitious goals, of course, so this is only a small part of the project, and we are only focusing at the moment on Erlang in this research. So these are the different skeletons that we are interested in. And Kevin talked about a nice example of putting a baking helmet on Joe. So this is a sequential code. There is an operation on a list of images. So this kind of data parallelism is very easy to exploit. So this is what we try to do. We try to see that this not as a parallel activity, like inserting a task farm to implement this operation. But there are different ways to make this code parallel. So for instance, we can introduce a pipe of two farms, as Kevin has shown us. Or we can also introduce a farm of pipes. There is a choice. The programmer must make a decision, and we would like to help to make this decision. So we'd like to predict potential speed up of each solution. In the paper, there are some measurements on the performance of these different kinds of patterns. There are patterns. What you can see here is that if you do things manually, then you can achieve a good speed up. That's which one? This line here. But all the others are somewhere around that. Sometimes better, sometimes worse. If you are smart enough, then you can do manually much better than a tool can do for you. If you're not that good, then maybe the tool is better than you. But using the tool is much simpler, much faster, easier. So maybe you are just happy with using the tool. So what are the main ideas here? We have to identify the components. That I call component something that can be executed in one worker node in a task farm, for instance. Then you can identify the different possible patterns of parallelism on that particular code fragment. And then you have to restructure the program so that you can insert a skeleton. And here you have to take performance estimations into account, or currently we are not doing this, but later we can take into account the energy consumption property as well. And of course, this is most conveniently achieved using refactoring tool. So POTI will allow us to locate parallel pattern candidates. They will be listed. Then the tool will somehow predict speedups for different configurations. This is also important because if you are using a large hardware system for a large software system, then you have to map parts of the software to parts of the hardware, so you have to somehow split up your resources among different tasks. So you might want to experiment with different configurations for a small component in the software. And then, once you have split up estimations, then you can try to propose solutions to the programmer, saying that, oh, this looks better than that one. Or if you increase the number of threads, then this becomes better than the other kind of effect. And of course, the tool will be able to have refactoring. And it's very important that if you use the tool, you get some confidence on what you do is legal. So we try to enforce some kind of semantics preserving transformations in the system. So what are the expectations for our tool? Clearly, if you use POTI, this will completely change the way you do parallel programming. If you have a tool like POTI, it will completely, automatically redesign your software application. It will be smart enough to introduce parallelism everywhere where it is necessary or beneficial. It will be very smart, and it will be able to predict that exactly the possible speedups. And of course, it will be safe. So you don't have to care. You don't have to worry about changing the semantics of the program. So this is false. Yeah. So, you cannot achieve any of these expectations. So you should not count on this. So, wow. You can find many places where you can introduce parallelism. You can, in many cases, find good estimations for the speed. And if you're a smart programmer, then it can help you a lot. So you can work effectively, more effectively than just doing things manually. And it offers some performance gains with relatively small effort. So this is what we tried. The whole stuff works within Emacs at the moment, but at some places, some pop-ups come to view. When we try to show where are the places in the code that you are able to introduce some parallelism, then you have a browser. So you have the feeling of Googling the code for parallelism. So you try to launch this software on a large software system, and you come up with some suggestions that, hey, if you insert it's very small, a farmer farms here in this line, then you will probably have more than 6 speedup with 12 processors. And if you select one of these suggestions, then you will see a more detailed view of the speedup calculation. So this user interface allows you to select where you would like to introduce the parallelism into the code. Of course, the tool tries to avoid to give too much information to you, because in that case you just trying to understand what's written there. It tries to prioritize its suggestions. So it tries to come up with the best suggestions first, and then if you are interested enough, then you can find other skeleton configurations in the list as well. And once you have selected a particular transformation, then you can use a code. You can use a tool to perform the necessary refactoring steps for you. Sometimes you have to do refactorings manually, but for many cases you have developed different automated transformations that you can choose from and apply. So what is the key idea behind this? It's very simple. We try to predict speed up by measuring the sequential execution time of a certain program component on randomly generated input, and we have a cost model. Apply the cost model, and then estimate the speed up. It's of course it's not a perfect model because the cost model is not very exact, but it does not have to. It will give you a rough estimation of the potential speed ups. So this is the big picture of the system. We have the Erlang source code here. Then we do some static analysis on the source code. We try to come up with the estimations. We try to benchmark the sequential version of the code, apply cost model, and estimate the parallel speed up. Then we rank the possibilities. We try to come up with the best solutions and present it to the user through the user interface. You have seen that before with the web-based user interface. And then the user can make a selection. It's always the programmer who makes the decisions. The tool is only helping out the programmer to make the right decisions. And then we have lots of automated refactories implemented in the refactoring engine, so the programmer is not left alone rewriting the code, but he can help in many places. So the first step is pattern candidate discovery, where we use various data flow, control flow analysis to collect as much information as we can about who calls who, where we use large data structures. Since we are focusing on data parallelism most of the time, we put an emphasis on these comprehensions and hydro functions on this like map. We also try to analyze map-like recursive functions. We try to insert task forms and pipelines on these comprehensions. Of course, there are many side conditions to check about, for instance, side effects or stateful components. And we also try to investigate different heuristics. So, for instance, if you know that the programmer already parallelized certain operations on a given data structure and you pass the data structure to a next computation, then you may think that this is a big data structure, so it may be useful to parallelize the other operation as well. So you can use these kind of heuristics. I have used the word component. What do I mean by component? It would be very nice to say that we have purely functional components in the system, but it's never the case in Erlang. So, of course, this had this nice paper finding out that there are no pure functional fragments in most of the Erlang code. So there is always some nasty things going on behind the scenes. So you have lots of sources for side effects. For instance, message parsing itself. But there are others. You don't try to say that you can only refactor something when it's pure, because in that case you would not be able to refactor anything. So we try to define the concept of hygiene. So a component is something that is more or less safe to execute in parallel with other components. Okay? It doesn't have to be pure computation. So we can say that this is a component, this will use resources, and it either doesn't use the given resource at all, or it uses it only for reading, or it uses also for altering. And then if you have a set of components, we can see if there are read-write conflicts or write-write conflicts within the component set. So this kind of analysis allow us to move the boundaries from purely functional computations to hygienic components. So once we have found the pattern candidates, components that can be run in parallel, then we try to do the costing. And as I said, we're going to use a cost model, but to feed the cost model, we need sequential execution times. So the tool must be able to automatically compute the sequential execution times for given inputs. So what we do is take a piece of code we have found there and invent some random data, feed that random data to that benchmarking component, and then let's see what we have. So it's we can do this with the refactoring tool, of course, because in the refactoring tools we have a nice representation of the program with the source code, lots of semantic information about the data flow and the control flow. So we can determine the free variables of a code fragment, and we can assemble a new module behind the scenes and just dynamically link that module and code. Generation of random input does not seem a very meaningful thing, but wow, it works for many cases, and of course does not work for other cases. So if we can generate good random data and we can measure good values, then we use it. If we can't generate good random data, or we can't come up with good sequential time estimates, then we don't use it, of course. So then it's the responsibility of the programmer to find those places in the code and do the realizations himself. So it's not always meaningful, but easy to automate. So we can use QuickCheck to generate random values of certain types. So that was for free. And since QuickCheck uses types, we need to type our expressions. Currently we use typer, but the success types are not really good for this purpose. So we have to invent some precise, more conservative types. We don't generally need more generic types for expressions, because we don't want to type the program. We just want to find legal values for a function, input values for a function. So if we have two strict types for function, no problem. We will generate stricter random input values. So it's acceptable for us. So once we have this sequential execution time, we will feed it into the cost model. We will present the best candidates. So we have cost models for different skeletons that was published 1 or 2 years ago already. But as you see, there are certain parameters in this cost model that needs calibration, like how much time it takes to copy a list node from one place to another, from one process to the other, or how much time it takes to spawn a new process. So we have to measure this on the given target architecture and use this calibration in the cost model. So this is why we have this calibration component in the system. And finally, we have this pattern candidate browser, which will rank the best realization candidates will be chosen by the tool. And it's not in Emacs; it's pop-up in Emacs, but the whole workflow is I think is pretty well integrated with Emacs. There are many things where we are weak at the moment. The whole system is in quite unstable state. So it's an experimental tool. It works if I love it. If the tool doesn't feel that I love it enough, then it doesn't work, of course. So you have to be very careful. If any of you want to party, just tell us. We'll show you how to party. I think personal assistance is the best at this stage, so we should have you to install the tool and use it. At the moment we focus on task forms and pipelines, but we would like to progress on other skeletons. It's very fast at the moment, so the pattern candidate selection is the slowest part of the process. So if you have a large code base, then you maybe have to wait a day or two to analyze it. Also, you have 2 million lines of code, then just loading this code into the system, well, it takes lots of time.
You can parallelize that.
Sorry?
You can parallelize that.
Well.
But at least it's automated right?
Yes.
If you didn't have this, you would be doing this by hand for a few days.
Yeah, so it's... I have more than 2,000 list comprehensions in the refactorer. So, yeah, it's not very convenient to parallelize all of them by hand, of course. So what's the conclusion? So I'd like to present you this party tool, which is building upon the existing refactoring tools for Erlang, Wrangler, and Refactorer. We use both. We try to make best use of both. It can find parallelizable code by discovering pattern candidates and predicting speedups. We have lots of refactorings implemented, like 40 to 50 refactorings available to shape the code and then introduce the needed skeletons, as Kevin showed you. But it requires help from the programmers. It's not a magical tool that you say that you want to have parallel code and then it will do everything for you. Sometimes you have to give hints, sometimes you have to have the tool to get the right results. So that's it.
So I wonder if your cost model takes into account intention for shared resources. I mean, if everything that you parallelize talks to the same gen server, then it won't scale well. Do you look for that?
Yeah. The customer is too simple to take this into account.
So how often does that become a problem? You don't get at all the speed up in your sector?
We have experimented with small case studies that it worked. Always, the customer overestimates parallelism force. So you have to know that, yeah, it says 9, well, it should be 8 or 7. You have to know that. Yes. For large software, we have no results yet.
So John, I think you can probably see this as an example of a cost model. And you can certainly get a better cost model. So in fact, we're working towards something where we're analyzing what actually happens in x86 when you run a program. We do have models to work at that level of detail, the exact machine level interactions. But I haven't quite got to the stage of function. But we can plug that in.
I'm not really asking about the details of overheads in x86, so much as a more general or higher level problem that there may be a shared resource that drastically limits power. So it'd be quite interesting to know, well, is that something which is going to hit you 30% of the time in large software, which makes it a really important research question? Or is it something that, in principle, it's a problem, in practice it doesn't matter, in which case one might research something else?
Well, as you saw from the first talk, the previous talk, for some resources it really does matter. So if you have a shared counter, you're accessing that all the time, that really hurts your performance.
Sure, but in real
for other
life,
resources, particularly if you have a good design. So one of the things we're trying to do here with pattern-based design is to limit the communication to maximize the dependency. If you have the right design, then contention is closely defined. It only happens, for example, in messaging exchanges. You can quantify that, you can minimize it, and then if your design is right, it doesn't have too much impact. Whether you can analyze all cases, like all those cases, other than the approach we're taking of going down to the x86 side, I'm not sure.
I look forward to the user results.
Do you guide the areas you try your refactorings by profiling the whole system before? So you won't refactor anything into parallelism that's called once and ignore the stuff that's called all the time.
No, at the moment we don't have statistics of execution frequencies of certain components in the system. Just look at the source code. So maybe it is possible to discover
Read
most
less
frequent
than-
parts of the code by just static analysis of the source code, but we have not done that. I think that would be more appropriate with collaborating with the runtime system. So you make experiments with the software,
I mean,
and then get the
profiling
information.
data
Yeah.
from one of the Erlang profilers, and like
It's not just the Erlang profilers, but in the peripheries project, a tool is being built to collect this kind of runtime information and provide it as a service to other peripheries components. And we will be able to use that once the interface is fit together. But I don't want to be counted there, but that's also a piece of future.
I think Peter's suggestion is very good, because if you're measuring large amounts of code, I think the number of possible parallelizations is exponential in the number of these higher order functions, these patterns that you're finding, because you can have arbitrary permutations of them. So if you somehow know where the 80% of the computation is happening, you can identify 20% of the code. That might make the tool a lot more scalable if you can focus on the big eaters, where all the work goes.
But it's not just that, Phil. You also have to focus on the dependencies. So as I showed with the wall building, although the block at the bottom of the wall may not be very big, if you don't build it, you can't build it the rest of the wall.
Sure.
And
So
that's important too.
when you measure where the computation goes, you need this kind of summative relationship. So when you evaluate this function, it induces a whole lot of work elsewhere.
Potentially. Yes.
I think we're out of time. Sorry, we have to. I'll leave off myself. So let's thank you for coming in.